guys, welcome back. I hope you enjoyed all the arrows that you had to draw for electron configurations. Sorry about that, but didn't come up with that. That's just the way it is. So we're going to be moving into another portion of talking about light. Now this section of electrons and energy is really fun. You're going to enjoy this a lot because this is kind of the pretty, the colors, the vibrant things that we talk about, fireworks, flame tests, things like that, the rainbow, Roy G. Bibb, all the neat colors that we see around us. You know, how are electrons affected by that? How do electrons contribute to these colors? So we're going to talk a little bit about that and go behind the scenes and see how color may be formed. Then we're going to do a really cool lab on flame tests that you guys are going to get to actually be a part of in terms of watching, but getting to see what everybody else is seeing. And then we're going to talk a little bit about prisms and how light is diffracted into its electromagnetic spectrum, and how elements really don't have the same electromagnetic spectrum. You can actually identify an element based off of the different colors that it emits when you look at it through a prism, because that prism actually diffracts those colors, or the colors of the electrons of that element, into specific wavelengths of color. And not all elements have the same diffraction of light, so therefore you can identify them based off their electromagnetic spectrum, which is really kind of neat. So we're going to be talking a lot about this in this section, okay? So let's get started. Okay, so what is white light? Okay, we know we see white light every day when we go outside and it's sunny. Even when it's not sunny, you still see light. You have this white light that's being produced by the sun. Now, you know when it rains, okay, when it rains, right after the sun comes back out, you've got all this water vapor still in the atmosphere. And when you have this water vapor in the atmosphere, that sun, the rays, the light rays, the white light from the sun actually goes through these raindrops. And the raindrops, the water, acts as a prism and diffracts that light into these specific wavelengths. Now, the great thing about white light has all of the colors of the spectrum. So that's why we see those beautiful rainbows, okay? Now, white light is composed of different colors that can be separated by a prism. So, if you don't have a prism, you can use water, okay? Because raindrops and water. So when you shine that light through, you're going to get a rainbow of colors. Roy G. Bibb, red, orange, yellow, blue, indigo, violet, okay? And they're all going to look as if they blend together. But specific elements don't necessarily have that. So when you shine or put them through a prism, these different colors emitted from elements on the periodic table, you're going to see lines of color, distinct lines, because these elements don't contain all of the colors of the rainbow. They only have specific energies associated with them, so they're only going to have specific colors associated with them. Now, sources of white light are the sun and regular incandescent light bulbs, not the fluorescent light bulbs that you see, the incandescent ones, the cheaper ones, okay? Those are white light. Okay, so electromagnetic radiation and energy. This is what we're going to be talking about in this section, okay? So light is electromagnetic radiation. All forms of electromagnetic radiation travel through space at the speed of light, okay? And they move at the speed of light at 3.0 times 10 to the 8 meters per second, which is incredibly fast, okay? Faster than what we can see. That's why to us, when we flip on a switch or we see light, it's instantaneous, because by the time we realize the light has been turned on, it's already come on, because it's moving at the speed of light. We cannot move that fast. We cannot see images that fast. So to us, it looks instant, even though it's actually a process and this light is actually traveling at a certain speed. Light is characterized by wavelength and frequency. Okay, so what is wavelength? Well, if you have a wave traveling, okay, like a sound wave or a light wave or anything like that that's traveling, you're going to measure from the middle of the top of the wave, and we call that top of the wave a crest, or when it's at the bottom, we call it a trough. So you're going to measure from the middle of the wave to the middle of a second wave, and that's going to be the length of one wave, which we call wavelength. You can also do it if it's in the trough position. You measure from the middle of the trough to the middle of another trough. That gives you the length of a wave. okay? All right, so now wavelength, when you're drawing the unit for or the symbol, the variable for wavelength, it's actually a Greek letter, but I just tell everybody, draw it like an upside down Y, okay? So when you're drawing wavelength, make it look like an upside down Y. It's the distance between two corresponding points on a wave. So like I said before, it's from the crest, the middle of the crest of one wave, to the middle of the crest of a second wave, okay? Or you could use the trough. The units that we will use for wavelength are meters or nanometers. Nanometers is equal to 10 to the negative 9 meters, okay? So it's more than it's about a billion, okay? A billion times smaller than a meter, okay? And a lot of times you're going to see things measured in nanometers. And just remember, it's a billion times smaller than a meter. Now, frequency. Frequency is, the unit for frequency is going to be a V, okay? And it actually has a little curve on it, because V is actually for velocity, but if you curve it a little bit, that's also the Greek letter nu. So it looks like a V with a curve. That's going to be the unit that we'll use for frequency. Now, it is the measure of the number of wave cycles that move through a point in space in 1 second. So how fast are these traveling? So what you'll do is you'll say, okay, start, and you'll count 1, 2, 3. How many times does a wave pass a certain given point in time that you're looking at in 1 second? That's what we talk about when we're frequency. So how many waves can you count that have passed through this given point in 1 second? Okay? The units that we're going to use for frequency are hertz. You should have heard those before. So think about radio stations. Okay, radio stations, TV, satellite broadcasts, they're all measured in hertz. Sometimes megahertz, kilohertz, something like that. But hertz is HZ, that's the unit that we use. Or you can use seconds. It's actually 1 over the second, or second to the negative 1. So these are the units for frequency. It's either hertz or seconds to the negative 1. All right, so now look at these waves. So if you have waves that are longer, okay, so the distance between them is greater, you're going to have a lower frequency. And that makes sense, right? Because when you're doing frequency, you're counting how many waves pass a given point in time in 1 second. Well, if the waves are further apart, not as many waves are going to pass through a given point. So that's going to have a low frequency. Long wavelength, low frequency. Short wavelength, high frequency, because the waves are closer together. So therefore, you're going to have more waves pass a given point in time in 1 second if the waves are closer together. Okay, so just it'll be important to remember that later. So low frequency, long wavelength, high frequency, short wavelength. All right, so differentiating the kinds of electromagnetic radiation. So amplitude. We won't really do anything with amplitude. Those of you that like music and are in band, amplitude is very important to you because you're looking at speakers and how high are the amps in that speaker is going to affect your sound, right? Well, we're not really dealing with sound. We're dealing with light. But amplitude is the wave's height from the origin to a crest, or from the origin to a trough. So it's how high does that crest get, or how high does that trough get? All right, that's how you're measuring amplitude. But like I said, frequency and wavelength do not affect the amplitude of a wave. So we're really not going to do anything with amplitude in this chapter. Okay, so now let's look at the forms of electromagnetic radiation. All right, so here we have different forms. Now, we talked about in the last section about nuclear, right? About gamma radiation. Well, as you can see, gamma radiation is all the way to the left of here because it's going to have the highest frequency. Because remember, when we talked about gamma radiation, we talked about how penetrating that power is, okay? So, which means it can penetrate almost anything. We can only block it with concrete or lead, right? So that's going to be your highest frequency, meaning they're going to travel the fastest, okay? Then you have X-rays. You know how you get X-rays on your arm. They're the next fast traveling waves. Then you have UV radiation. We've talked about that when we talked about the sunscreen and how dangerous UV radiation is on your skin because those waves are traveling at a high speed, meaning they're going to burn your skin. So it's very important to wear sunscreen to kind of filter some of those rays, or sunblock to even block some of those rays. Okay, so there's your UV radiation. Now you have your visible light, right? Your visible light. Right down here, remember we talked a little bit about that. Roy G. Biv, meaning violet's going to have the shortest wavelength, but the highest frequency, and red is going to have the longest wavelength, but the lowest frequency, right? So the order that visible light is, it's Roy G. Biv, right? Red, orange, yellow, blue, indigo, violet. Red being the longest wavelength, lowest frequency. Violet being the shortest wavelength, highest frequency when you're talking about visible lights. Then you have infrared, okay? Remember those infrared goggles, right? That you can wear, those night vision goggles. Then you have your microwave radiation, and then you have your radio frequency. This is because the frequency is so low and the wavelengths are longer, that's why we can pick up radio stations very easily, okay? And that's because the frequency is so low that it allows us the opportunity to get those stations in, and it has a longer wavelength. So we can actually use antennas to pick up that radio frequency. Okay, so as wavelength increases, frequency decreases. They are inversely related. Okay, and remember, frequency is in units of cycles per second, or 1/2 seconds to the -1. Okay, here's another example of your wavelengths of visible light. Roy G. Biv, remember? All right, so this will be the last slide we're going to go over today. The wave model of light cannot explain why heated objects emit only certain frequencies of light at a given temperature, or why some metals emit electrons when light of a specific frequency shines on them. Scientists realized that a new model or a revision of the model of light was needed to address these phenomena. So we're not going to get into that today. We're going to get into it later in the week. But what you're going to have next is you're going to be working on tomorrow. You're going to be working on a POGL. You're going to have to color that in, and you're going to have to answer those questions. You will have a quiz over the POGL. So it's important that the first thing you do is go ahead and fill out that POGL that I've given to you guys. The POGL itself is not for a grade. Where you're going to get your grade on the POGL is in the quiz. You can use that POGL on the quiz, okay? So it's very imperative that you fill that out. If you have questions, all you have to do is email me and I'll help you with the POGL, okay? But then you'll take your quiz, and then Wednesday and Thursday, you guys are going to get to really see the lab that the students are doing in class. It's a phenomenal lab. You're going to really enjoy it. We're going to make it as real as we can, as if you guys were standing in the room yourself. So look forward to that, because there's going to be a lot of colors, a lot of neat things that you're going to get to see with that lab. All right? So I will be back talking with you on Friday when we're going to talk about the quantum concept in your notes.